Okay, welcome to Computer Organization. Today we're going to be looking at the binary representation of numbers. There's a couple of terms we're going to be looking at today. There's bits, bytes, binary, decimal and hexadecimal. Some of those you should already be familiar with, some may be new to you. Okay, we'll start off by looking at the binary digit, or the bit. It can have one of two values. It can either be a 0 or a 1. We've already looked at the bit and we've already looked at the byte. The byte is 8 bits. Okay, and we write the bit as a small b and we write the byte as a capital B. So the screen there, 8 small b equals 1 big B. Okay, 8 bits forms a single byte. As said, the binary is the number system used by the computers, and it is in base 2 because we can just have 2 digits, a 0 or a 1. Decimal, that's the number system we normally use day-to-day life, and it's base 10. We've got those 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 digits there for us. Hexadecimal, we'll spend a little bit more time with that maybe in the next class, but it's base 16, and we use that quite a lot in computing science because 16 is a power of 2, and so it's quite a useful one for us to actually be able to use. It makes a more concise form of binary. But what we're going to look at today is binary number systems. There's a video here which you can play by yourself. I won't bother playing it now. You can listen to that on your own time. What it talks about though is a positional number system, and that is what our decimal system is. And so long as you can understand the idea behind a positional number system, understanding how binary numbers work becomes much easier. So essentially, the position of the digit has meaning. If you write out these two digits, 4 and 5, it's just not random 4 and a random 5 in that position. They actually have extra meaning. The 4 means 4 lots of 10, whereas the 5 means 5 lots of units, so it's 45. If I was to invert their position, write as a 5 and then a 4, I'm getting a completely different number. I'm getting 54 instead of 45. So the position is really important. And the position in a decimal system increases by powers of 10. So in our units, that's 10 to the power 0, which means 1. In the next column, it's 10 to the power 1, which means 10. In the next column, it's 10 to the power 2, which means 100. And we have exactly the same idea for binary. So here is a binary number. As I said, it's the same as our decimal in that the position of those digits is important. If I look at the rightmost digit, this is often referred to as our least significant bit, it's a 1. And as I start to go left, I've got a 0, a 0, a 1, a 1, a 0, a 0, a 1. It's a palindrome, so if I wrote from left to right or right to left, I get the same number. But the important bit is, just like our decimal system, if we go on to our right, that is, if you like, the lowest value. You go to our left side, that's the biggest value. So we're going to have a look and see how can we convert this binary number to decimal, because we as humans use decimals. Computers love binary. So here's the number again, 1001, 11001. So I'm going to set up the positions. What are these positions worth? Well, because it's binary, we go in powers of 2. So I've set it up to, again, starting from the right, going to the left, 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5, 2 to the power 6, 2 to the power 7. I've got 8 bits there, 1 byte. The values of those I've written in the next row. So 2 to the power 0 is 1. Then it's 2, 4, 8, 16, 32, 64, 128. If you're good at doubling, that's all you need to do. Now the next row, I write the number down. So I've got 1, 0, 0, 1, 1, 0, 0, 1. That means I've got Again, starting from the right, I've got 1, 1. So I write that down in the last row. I have no 2s, so I wrote a 0 down there. I have no 4s, so I write a 0 down in that row. I have 1 8, so I write an 8 down there. I have 1 16, so I write a 16 down there. I have no 32s, 0. No 64s, 0. And I have 1 128. So now, what I say is I take 128, add to that 16, add to that 8, add to that 1, and that gives me 153. So 1001, 1001 to base 2 is the same as 153 base 10. So that looks at how, if we've got a binary number, how to get the decimal equivalent out from it. So what we'll do next is we'll take a decimal number and we'll work out how can we get the binary equivalents. So we'll start with the same number, we might as well. I take 153 and I subtract 128 from it. Why 128? Because that's the largest number that is smaller than 153 that I've got. The next number from 128 would be 256, which is a little bit larger than 153. So I subtract 128. That leaves me 25. So I now go through and I think, well, can I subtract 64? No. Can I subtract 32? No. Can I subtract 16? Yes. So I subtract 16 from it. That leaves me a 9. Okay, next number, 8. Can I subtract an 8 from it? Yes, I can. That leaves me with a 1. Can I subtract 4? No. Can I subtract 2? No. Can I subtract 1? Yes. So what I have there is I have 128. So that gives me, if I now start writing out from the left side, that gives me a 1. I have no 64s, 0. No 32s, 0. 116, 1. 1 8, 1. No 4s, 0. No 2s, 0. 1 1, 1. So I get 1 0 0 1 1 0 0 1 in base 2. So that's how we can convert from decimal to binary. We still really need to have, to help us anyway, this table of numbers. So if you ever get sort of asked to do this, whatever reason you need to do this, write out that list of numbers double, 1, 2, 4, 8, 16, 32, 64, 128. Just remember, if you write it out, write it from the right to the left, rather than from left to right. Otherwise you'll get your binary number reversed. So write it out the way I have written it out, and that will help you to solve problems converting from decimal to binary and from binary to decimal.